I am really delighted to introduce Rachel Kranton. Rachel is the James B. Duke Professor of Economics at Duke University. Are they related?
James B. Duke and Duke, yes.
I thought so.
It makes sense.
Rachel studies how institutions and social setting affect economic outcomes. She develops theories of networks and has introduced identity into economic thinking. For those of you that don't know, Rachel got her PhD here at UC Berkeley in economics in 1993. She's taught at the University of Maryland, and she joined the Duke faculty in 2007. She has awards from the Russell Sage Foundation, the Institute for Advanced Study in Princeton, the National Science Foundation, the Canadian Institute for Advanced Research in the Social Interactions, Identity, and Wellbeing Program, and she was elected a fellow. Oh, she was also awarded a Chair Blaise Pascal, which is an important award in economics, I think. And she was elected a fellow of the Econometrics Society in 2012. She co-authored a book with George Akerlof called Identity Economics, which introduces a general framework to study social norms and identity in economics. She's also written extensively on the economics of networks, developing formal models of strategic interaction in different economic settings, and she has a long-standing interest in development economics and institutions. She focuses on the costs and benefits of networks and informal exchange, which is mediated by social relationships in these rather than markets in these contexts. So you can see the common thread, and I think she's going to pick that up and talk to us today about strategic interaction and networks. So please join me in welcoming Rachel.
Thank you very much. So thanks very much for having me. So a couple of orders of business before we begin. If anyone wants to move up, you know, everyone sort of goes towards the back. Can you guys get me? We're okay? Okay. Then another order of business is that in economics departments, people interrupt after I say one word. So I'm going to feel really awkward unless you guys ask questions as we go along. So these don't only have to be clarifying questions, they can be objections, they can be ideas. So, you know, this is a back and forth as we go along from the beginning. So it's not going to be a talk with one part and then a question and answer session. So please interrupt me as I go along. Okay, so I should introduce my co-authors. This is work with Yann Bramoulet, who is actually now, he's moved to the University of Marseille. He was at Laval. He's sort of in transition. And Martin Damour, who's a PhD student. And this is a long-standing research program that I have with Yann on strategic interaction and networks. And I'm going to give you a sense of what this program is about, as well as our new results, which we're extremely excited about. Okay, so first of all, what are we doing? We are studying game theory and networks. So let me give a sense of what those are. Game theory, I'm sure you all heard about game theory. What we're doing here is studying people taking decisions, but they're taking into account what others may do. So that's what we mean by game theory. That's what strategic interaction is. And what's new is that the network, there is going to be a network which structures who interacts with whom. So it can be different firms who are located in the same region. They're the ones that interact with each other. Friends interact with each other. Neighbors, literally neighbors in a neighborhood may interact with each other. So it could be a social structure or a geographic structure. And that's what tells me whose actions ultimately affect what we're going to call my payoffs, what I get from what I do. Okay? So the vocabulary we use to describe a network, there's variously used: interaction matrix, network, or graph. It tells you which, we use the word agents, which agent I affects which agent J's payoff. So if I'm friends with somebody, that friend then affects me. Okay? Now, this matrix network graph is a mathematical object. It's a matrix, right? And the entries of this matrix say who interacts with whom. Okay, so all it is a matrix. But when we introduce this matrix, it means that one person does not interact with everybody in exactly the same way. Okay? So one special case is indeed that everybody does interact with everybody all in the same way. And that's typically what people have studied. Bringing in the network where I may interact with one person and not interact with another, right? That's a new social environment and completely changes the incentives. Okay? And so we want to understand how the network structure changes the way people interact with one another in these settings. Okay, so the objective of this kind of analysis, so it's going to be a mathematical model of people making decisions when those decisions of mine affect your payoffs and your decision affects my payoffs in this network way. We're going to be solving for outcomes or the patterns of play as they relate to the network structure. So the whole point of introducing a social structure or a geography is to see how that social structure or the geography actually matters to what happens. Okay? And the words we use to describe these outcomes are things called Nash equilibria or stable equilibria, and I'll give you more definitions along the way of what that exactly means. But again, the point of this whole exercise is ultimately we want to generate insights and possibly empirical predictions about what people may be doing in different environments. So I'm going to, one point of doing this kind of work is to say, gee, I never thought that if people were interconnected in this way, then we might have more public goods provided rather than less. So that's an insight. Then there's actually, we are going to generate empirical predictions, which is say, give me a matrix. So we all know what a matrix is, this mathematical object. I'm going to calculate some numbers that relate to this matrix, and that number is going to be key to the possible outcomes which emerge. Okay, so if I have data, if you actually have data on the network, then you may have a prediction about the actual actions people will be taking. Okay? So this specific paper is looking at a class of games. So when I mean a class of games, it's a class of games that all share a particular mathematical structure. The best replies are linear. I'm going to describe this all later. The point of this bullet point here is to say that these are extremely complicated objects, these games on networks. Okay? And so in order to make some progress, what we've done as a community is we've looked at little subsets of problems. Okay? So I've looked at buyer-seller networks, I've looked at insurance networks, I've looked at a variety of different networks in specific applications. And what this paper does, which is new, is actually makes the observation that all of these settings, which we were examining one by one, they actually all have the same mathematical structure, so that we can actually build a unified theory about these settings. And so here are some of the settings that this particular class of games covers. So all of these were done sort of in isolation, and the sort of starting point for this research is, they're all the same math. It's all the same math, so I can look at this in the same way. And again, I'm going to give you examples of this. And so we find the outcomes or the equilibria depend on this new measure of this matrix, and that's the lowest eigenvalue. So some of you may or may not be familiar with matrices and eigenvectors and eigenvalues. There's basically, you want to think about them as statistics or measures of a matrix. Okay? So this is a particular, you give me a matrix, I can put it in a computer and it can calculate a number. It can calculate the highest eigenvalue, the lowest eigenvalue, and so on. So our results are going to depend on this lowest eigenvalue. And again, I'm going to give you illustrations of what that means as we go along. But this is the main theoretical result, right? So in the community of economic theorists, when they see this, they say, wow, we're actually looking at a unified theory, okay, that we're able to cover a lot of different circumstances with the same model, with the same framework, and we're actually able to come up with a relatively general result, which is, give me any network, and I can give you a prediction. Okay? And so then I'm going to give you examples of this along the way. But this is the sort of contribution that this paper makes to the world of economic theory. Okay, so now let me give you a sense of the motivation behind this research, why I got started, what are the types of problems that this network model can capture. So the impetus for this work was looking at networks development and the adoption of new technology. So many years ago, it's maybe a long time ago, when Jan and I first started talking about research ideas, we kept on thinking about this example. So this is an example from India, and it's actually, we have data on what happened in India. This screen is too high for me to use my arms. Okay, so HYV stands for high yield varieties. So you may know about the Green Revolution in India when new plants and new seeds were introduced that produced more corn. So you get 3 ears of corn per stalk rather than 1, right? So these are high yield varieties. It's a new technology, and it was introduced into India in the 70s. And what's interesting is to see is who adopts this new technology and when. What are the patterns of this adoption of this new technology? And Foster and Rosenzweig, or a set of economists, have data on adoption of this new technology. And what they observe is that this technology is not adopted all at once, but there's actually a spatial distribution of adoption of this new technology. Okay? Now, of course, adoption of new technology is out there in the literature. We know Coleman has that famous work on tetracycline. When did physicians in the United States start to prescribe tetracycline? He also has a network interpretation of that. Of course, we know that there's iterations after that which say it wasn't really networks, it was, so on. So I know the work that has come after that, which says that Coleman's original conclusion was not correct. But he introduced this idea. So I'm putting up here as the idea that the structure of the social relations among the physicians could lead to the adoption or not of particularly new medical techniques or drugs and so on. And what's interesting in this paper by Foster and Rosenzweig, I'll talk about it a little bit more in detail, is they actually can show this geographic, so here it's a geography rather than a social network, that there is a geographic pattern to the adoption of the technology. Now, both of these examples, so the idea that there is a new technology out there to be used, or a new drug out there which can be used, it's not just that the technology appears and people can use it. This technology has to be adapted to the local environment. So that's where we get into the point that this new technology comes along with the necessity of investing in public goods. So what I mean, so take this high yield varieties example. This new seed is introduced to the Indian countryside, and it needs to be adapted to the local environment. How much fertilizer needs to be used? When should the crop be irrigated? Okay? And these high yield varieties actually required much more fertilizer and much more maintenance than traditional crops. So this is a problem. They're great, but then they require a lot more complementary inputs applied in certain ways and so on. So the using of this new technology by a particular farmer and his experimentation with different combinations of inputs and fertilizer and so on is generating information not only for him, but it's public good. It's a public good. He's now saying this particular crop and this particular seed in our particular corner of the world needs to be used in this particular way. So this is an example of a public good, right? So this information that's being generated about this new high yield variety seed is a public good, but it's a local public good. Okay? Yeah.
That assumes that the person shares it.
Absolutely.
Yeah. So it may not be a public good. This farmer may just hoard information.
Right. So exactly. So in India, we see there's evidence that people were able to observe what other farmers did. So absolutely, I'm going to be talking about a public good, which is indeed a public good. And it's not a private good. It's non-excludable. Actually, I was going to give a little definition of public goods. But the key thing that I want to mention right now is that it's a local public good, and that it's going to depend on who can actually access that new information, right? So it's the public good. It's excludable, but only incompletely, right? So it's wonderful. I get to put up Halvarian's name here. So one way you want to understand this work is to take the Bergstrom, Bloom, and Varian paper, which is about the private provision of public goods. This is not government provision of private goods. This is private provision of public goods. Individuals are doing this, right? Individuals are creating this new information, adapting this new technology. Their work is on the private provision of public goods. What we're taking is taking this private provision of public goods and putting it on a network. So we literally can take the modeling that Bergstrom, Bloom, and Varian have and have a network version of it. Okay? All right. So I was going to go a little bit into what we mean by public goods and so on. So public goods are typically understood, which are goods which are non-excludable and non-rival in consumption. So some classic examples are clean air, national defense, public parks. Public parks is on the edge there because if a lot of people show up at a public park, then it becomes too crowded. But the idea is that my breathing of clean air does not inhibit your breathing of clean air. That's a public good. Okay, that's the classic notion of public good. Yes?
So getting back to Anna's question of whether or not the farmers share this kind of information, so it may not be always the case that that sharing of that information is non-rival. For example, if my yield increases, that might have an effect on the local market price.
Absolutely.
Which means that,
right.
Yeah,
right. Absolutely. So, and that type of thing we might be able to include in our modeling, right? So we're going to see that I might be able to put weights on what I mean by literally a mathematical weight on you and I rather than me and Dean Saxenian. You know, so we can incorporate those ideas. So this public good may be more or less transferable, more or less perfect, and these are things that we can model. Absolutely. Yeah.
Just in anticipation of what comes next, is the notion of network that you're using here that of the interaction matrix that you talked about before?
Mm-hmm. So those four things I put up, interaction matrix, network, graph, they're synonyms.
So you're not like talking about like game theory or like network formation or traffic across a network or anything like that, right?
No, so it'll be really clear exactly what I mean. This is the beauty of modeling. You know, why we do these models is I'm going to show you exactly what I mean by network and exactly what I mean by interaction on that network. And just to answer one part of your question precisely, the network is going to be fixed. I'm not going to be thinking about people forming friendships, forming links. The network is fixed. These Indian villagers live in particular places, and that's fixed. Okay? And then I'm going to be thinking about what they're going to be doing given their positions in that network. So there's the clock in the room. I want to make sure that I'm keeping on track here. Okay, very good. So this is the classic notion of a public good. This is the classic thing economists talk about. We're adding the aspect of networks. Networks is going to allow us to capture the idea that there are many goods which are non-excludable only along social or geographic links. So some examples of this might be, again, clean air. Here you think of, you know, if you're polluting a factory in one direction, it's the people in the other direction that are benefiting from the clean air. Irrigation systems and information innovation. And of course, I'm going to be talking here about the main example, and which indeed started us on this whole project, is innovation and information flow in networks. So there's obviously many, many examples of this. Consumers benefit from the experience, the research of friends and family. So when I want to buy a new car, I ask some guy in my, actually a colleague who loves to follow new cars, and he can recommend to me which car I should buy. In industry, there's a lot of research which shows that research and development findings spill over to other firms, and empirically these spillovers are often local. So you see these among clusters of firms, that certain firms are learning from other firms but not further distant firms. I've just talked to you about agriculture, medicine. People are learning from other experiences with the new techniques. So I want to give a quote from the Foster-Rosenzweig paper that I just told you about. So if you read it, it says, a farmer can reduce his losses in a given period if he can rely on his neighbors to gain the relevant experience, and then increase his use of the new technology as it becomes more profitable. Okay? These results suggest that information on the management of HYVs within the village is not excludable. Okay, so they're looking at the data and making this conclusion. So this is the question of how much are people able to see what their neighbors are doing. And that fact that they see this geographic patterns is indicating that there is some non-excludability. But again, given the geography of the village. So the message we can get from this work is that information is non-excludable. There is some public good aspect of this search or this experimentation. So these farmers sort of doing this experimentation with this new technology, the information is non-excludable, but it is the physical and social geography of the village was important to that. Yes?
Yes, I mean, implicitly, if it's physical, it seems to me like one, it could be you can observe,
Mm-hmm.
and right, so is this observational, or is this about information transfers between different people, or did they
Okay, so they're silent on that. So they don't actually observe farmers' conversations with other farmers.
No,
Oh.
a farm, right, so I see what my neighbor did, and his plants are growing, and I'm like, I saw him out there watering extra
Right.
fertilizer. He actually has no interest in sharing with me, he hates my guts. But
Right.
he can't
Right.
stop observing it like when he wants to put a bigger fence, right?
Right.
Another is, everything that he did was not observable,
Mhm.
and the only way in which it was shared is that he chose to disclose it.
Right. So they don't make a distinction. We don't have any information on the distinction between these two.
It would seem that that's important, because one of them is
Abs-
about proximity, and the other one isn't.
Absolutely. So in some sense, this is a limitation of the data, right? We don't know. And there are people who, as I'm sure you know, who are going around and asking, who do you talk to? Who do you talk to about farm information? Who do you talk to about family issues? Who do you talk to about money? I mean, now there are people who are now surveying networks of different forms, right? And so, of course. So I'm presenting this as an example of a public good aspect of information. And it's one example of a local public good. Okay? And so I cannot give you more information on exactly were they chatting about it or were they peeking over that picket fence.
So the data is just the observation that they adopted.
Yes.
Somehow they adopted.
And what they observe, the data is actually is the amount of land which was devoted to the particular crop. Yeah.
Just do the particular modeling choices that you made and what's coming up fit both of those cases that Julia was just asking about? Or
Yes. In fact, yeah. It's going as long as the results, as long as what I do impacts your payoffs, right? And that we think of that as the public good. So I experiment with this new technology, and the amount of my experimentation, you benefit from it, more or less. So I'm going to have a parameter to make it more or less. Then I'm fine. So I don't have to know whether it's the picket peering over the picket fence or not. What I don't model, which would be sort of a next step in this agenda, would be trying to stop somebody from observing what I do. So I'm just having this flow be there. It's an exogenous flow. Okay?
It's not observable. And this is
Right, I think Anna's question too is that surely I could go to great efforts to limit the extent to which my knowledge is contributed to the public.
Yes.
Right? And it could require different sorts of interventions depending upon whether
Yes.
or not they're observing
Sure.
it or it's. And
Sure.
so it
I agree
seems
with that.
The information certainly is useful to the public, but I'm not quite sure why in this context it's a public good. I mean, I could exclude.
Well, so again, the presumption is that it is a public good. Okay, and so you may argue that it's more or less a public good. What the presumption is suppose that it's public between these particular set of neighbors. So it's not completely public. So that's already a restriction on public goods, is that we're saying it's not open to everybody. Not everybody knows this. It's only open to my friends, who I chat with, for example. Okay?
It's confusing because information is very excludable. We can't, many ways to
I'm
exclude
sure
people.
maybe John and Anna could help me frame it.
So I think the picture can be a lot more complicated than that. I mean, if you think about Monsanto and their business practices, you can introduce a third party beyond these agents who are farmers,
Right.
who can do coordination and things like that. So I think what Rachel is doing here is actually a stylized model with one particular example to illustrate the dynamics that
Right.
can arise.
Right.
But
What?
this is just one, so we shouldn't get too hung up.
Yeah, so I guess I should say that the data in several studies tells us that information, you might try and stop it, but you can't stop it completely. That might be another way of understanding this. It depends on how you want to view it. You can't stop it completely, or or it's completely there. I'm going to have a parameter which tells me you could stop it completely. You know, we can look at that case. It's a pretty boring case, right? It means that I'm only there by myself and nobody else is there. But I have that in my model. And then I have the extreme version where I see absolutely everything you did. So you know, if you want me to work on those dimensions, we have results for the whole range. From where I'm all by myself, I'm producing by myself, nobody sees me, nobody sees me, I don't see anybody. That is a special case of what I have. Then I can see you a little bit, teeny bit, you know, really close to 0 bit, and then I can see everything. So that's, we have the whole range. I want to say that there is, the citations are in the paper, but in industry, as maybe they do want to block it, we also know that there are spillovers. So we can't stop, the firms, why they might not to, cannot stop it completely, right? And we know okay, so, all right, so.
For my own example, I think the most likely and plausible explanation is that they buy from the same shop, and that's much more difficult to block, and that's the conduit for information. So that might be that discontinuity of the data. You might be able to find that discontinuity of data of people who shop at the same place.
Yeah, that would be actually very interesting, right? Because in some sense, again, going back to what John said about the stylized model, in some sense, I don't need to know exactly how they get the information. I just have to know it's that these people know each other's experimentation results. That's all I need to know. The actual social mechanisms by which it takes place are extraordinarily interesting, right? And so we might want to delve into that, because if you want to intervene, well, maybe it's the shopkeeper that we should be talking to.
So your point
right.
is that the sharing of information is really, really important to the diffusion of the product. In a successful
Well, and actually to the incentives to actually experiment to begin with. So let me jump to this bullet point. Okay, it's coming up. So what are the types of research questions? And here, who's providing this information or this public good? And here's what I want to get at. Do people innovate themselves, or do they free ride? Hey, if my neighbor's going to do all the work, why should I do anything? Right? So the fact that information flows, the fact that there is a public good, right, means that there could be less incentive for people to actually provide the information themselves. So this is the classic public good problem of free riding on a network. That's what we're doing. Again, go back to Bergstrom, Bloom, and Varian. It's a classic public good problem on a network. Information is one example. Again, as I emphasized, the modeling fits a wide range of economic contexts. Okay. How does the network affect the provision of information? So we want to know who's free riding, who's doing it, and overall, if the network is, say, more or less connected, do you get more or less experimentation, or more or less information being provided, more or less public good being provided? Okay? And how might new links affect the provision of the information? So if I introduce a new shop, maybe that's the mechanism, and then all of a sudden, you know, two people who never saw each other's faces in the village all of a sudden do. How does that affect the overall level of experimentation in this village? Right? So we want to, say, manipulate this network a little bit and see what emerges. So this paper is really combining both innovation and social learning. So a lot of work out there in economics studies innovation and studies social learning, but not together. Okay? So first time, this is the bullet point I wanted to get to. It's the first time these two features appear together, and then, of course, we have the network as well. So it is individually costly to generate new information, and information flows to other people, and the fact that the information is flowing to other people, you're not capturing the full benefits of your own experimentation. You may have less of incentive to do it because, of course, it's individually costly. So it's the classic free riding problem. But again, what's interesting, if you look out there in the work on innovation, there's a lot of work on innovation, there's work on social learning, but actually realizing that information flows, we all know information flows, but what does that imply about the incentives? Right?
Economics people don't talk about it.
Yes. Sorry, these are, First time two features appear together in an economic model. So I am, I hope I've conveyed to you all day long how much I appreciate the work outside of economics. So I know. There's probably, right. But you guys don't have the eigenvalue yet. So, so the idea of the information flow here is, again, these contexts, I've learned an enormous amount from people outside of economics. The idea is now, hey, we've listened, we've got it, I'm going to now bring this stuff into my models, and you know what? I found out that this cool thing called an eigenvalue matters. And this eigenvalue, which is you have data on a network, you calculate this eigenvalue, you may have a new prediction. Okay, so that's how I sort of see this process. This is more complementarity rather than rivalry. Yeah.
So by social learning, you mean information spreading from one individual who experimented to others?
Exactly. Right. Okay. Great. So one of the things that's going to be challenging in this work, in the mathematics, is that public good provision is what we call strategic substitutes. So imagine you have a network, and a path in a network is literally, say, a path between people. And I just show you a picture. This is a path, right? So imagine that you can imagine that there's links, spreading out from all over this graph. And this is one path from one guy on one side of the village to a guy on the other side of the village. Okay, so imagine that. So let me switch applications just for fun. Imagine this is literally a neighborhood street, and this is we're worried about people planting gardens. So gardens is another sort of classic public good, beautification of a neighborhood or so on. So imagine that the person in the middle of the neighborhood plants this beautiful garden, and this is not a competitive gardening community. It's not like everyone wants to out-garden the other person. It's actually people enjoy the gardening and the greenery produced by their neighbors. And I say, well, gee, my neighbor planted these beautiful trees. I'm going to enjoy them, and I'm going to do less of it. Right? This is, again, public good. Okay? And then their neighbors are going to say, boy, they let their lawn go to, their lawn isn't being well kept up. I really want some beauty around me, so I'm going to do more. Okay? So I could do this in the Foster and Rosenzweig example as well. I just wanted to say there can be other, there's other examples of this. But what I want you to see is this up and down nature of public good provision. It's substitutes. One person does more, his neighbors do less. It means his other neighbors do more. Neighbors, by the way, is also the technical term for people who are connected in a graph. So I can introduce that vocabulary. So one agent does more, his neighbors do less, the other neighbors do more. You have this up and down nature that actually makes it mathematically hard to think about how things settle down, right, into what we call an equilibrium. Okay, so strategic substitutes is a particularly complicated setting to work with. So that's another thing that we're doing, which is new, is we're looking at environments where strategic substitutabilities are at the fore. Yes? Absolutely. So, yes, absolutely. So again,
Example would be just one comment. If you have an operation system and people produce applications for that, the more people adopt this operation system, the
absolutely.
more applications will be produced and the more people would like to do it.
Yes, so absolutely. So again, this is where modeling can really help us, because when I write down my network, I'm going to have this matrix, and I'm going to have values for each entry in this matrix. And that entry could be positive or negative. And if it's positive, it's going to indicate a substitute. If it's negative, it's going to indicate a complement. And I can have any matrix you want. Okay? So I can incorporate complements and substitutes. Why I'm emphasizing the substitutes case here is that if you have a setting where it's all complements, it's really easy to solve. Okay? Yeah, so you know that. You introduce a little bit of substitutes. Yeah, no, even any bit of substitutability, you're out of the worlds that have been studied before. But we can talk about it, okay, given the games that we have. Now, I'm emphasizing all the substitute case to kind of make that point as to why it becomes complicated. It's because these ups and downs. I'm sorry.
Standard analysis that whole variant is done on substitutes.
Yeah, but it's not on a network. That's the point. It's the network aspect of it. Sure, this is Bergstrom-Bloom invariant on a network. That's exactly what this is, this paper. Okay? And it's the network which is new, and it's the network which makes these things complicated. And the network can represent substitutes between some people, complements between other people. I have complete freedom to specify that. And again, that's what makes this model general. Okay, so it's stylized, but yet general. Okay? All right. So I didn't tell you the result. So when we're in the environment we look at, we're going to show that the outcomes which emerge in this equilibrium sense, which I'll describe later, often involve this extreme play, meaning some people planting the huge garden and other people's not doing much. Or back to the information example, some people providing a lot of information and other people free riding on the provision of that information. And what kind of outcome we see is going to depend on this object, this mathematical object, which is an eigenvalue of the graph, and in particular, the lowest one. Okay? And again, I'm going to show you examples of how that works. Now, I talked about how I'm going to want to look at what we call comparative statics. So I want to change the graph just a little bit. So suppose I made this guy here linked to that guy there. So I added a link, right? So I added a village store somewhere. What will happen to the overall provision of the public good? And we can show that, okay, so what's going to happen here is some agents are going to increase, others are going to decrease. Because as I add a new link, wow, people get more information. They might have access to another source of information, which is good, but it actually reduces their incentive to produce information, right, or plant the garden, whichever one you want. So what's on aggregate, what happens? And we can show that the overall actions are going to decrease. So I'm going to show you examples of that as well. So as you add links, you're going to have an overall lower provision of the public good.
So am I to understand your matrix as just an adjacency matrix on the graph?
That's all it is.
Okay.
It's just a matrix. Right, exactly. So the other vocabulary, what's interesting about this field is that each little discipline has their own vocabulary for exactly the same mathematical object. So these are nodes and edges in the adjacency matrix, and that's what it is. Okay, and I call it a matrix, and I call these agents, and I call them links, but it's the same thing. Okay, yes?
So adding a new link is like making a really good lecture on a MOOC, so you don't need all the individual safety notes because everyone can.
Right, and so then we're going to have a question about welfare. Is that good or bad that we only have one person actually producing the lectures?
Depends on if you're a professor.
Yeah, right. So yeah, well, we're going to talk about that. I'm actually going to show a little example of that. Yeah.
So did you just say that in the super friendly village where everybody shares with everybody, that there actually would be lower overall adoption of HYB, for instance?
Could be.
That's surprising.
But it's basically is that, nobody has the incentive. So nobody has the incentive to do the innovation on their own. They're all relying on one person.
He decides not to do it.
Sorry? What?
He decides not to do it, maybe.
Right. Well, then it's not, but then in equilibrium, it won't be that nobody does it. Right. There will be some limited amount, but it won't be as much as if people were separated. In fact, the biggest. Think about what public goods are. If you're all by yourself, you got to do it all by yourself. Once you connect somebody, well, then you can share it. So you can see that these things are going to.
Is that why the government then steps in?
One could view this as a market failure, right? It's public. Well, first of all, we know that the classic reason for government intervention is to provide public goods because there's under-provision of public goods by private citizens. So national defense is something that we don't, can't all go, well, anyway, let's not get into that discussion.
Yeah. Could you argue that the incentive structure in those circumstances would be wrong for the individuals to do it, so you need the government to do it?
Yeah, so absolutely. Anytime, so we're in so I don't do this analysis here. I'm not going to show it to you, but it's very easy to conduct. Anytime you have a setting where the individual's actions, so I create something, whatever it might be, and lots of people enjoy it, right? But I don't reap the full benefits of what I do, then the theory, economic theory, would say there's under-provision, right? I'm providing too little of it. Now we know that people actually, wait, I'm going to get to it. We know that there's a huge amount of voluntary contributions to public goods, and we know that there's many, many examples of people providing public goods. We know Wikipedia and so on. We know that there are all these examples, and I'll tell you what's wrong with the models. The model that I just described, what's wrong with it is the payoffs that we're attributing to the individual. They are utility function, right? And so we've misspecified the model. we've misspecified our model of individual behavior. Okay, so the classic model of individual behavior has me worrying just about my economic returns and none of these other things. And so we've misspecified that. Yeah, prestige, status, and so on and so forth, and identity, if I can at least get that word in here somewhere. Okay.
Even just on if all I'm interested in is the economic return, I need the information not for the sake of the information, but to produce the crop. And it's contributing as much as it possibly can in my production of the crop. And I actually am not losing because other people are producing the crop, unless we start modeling, if I'm not eating all the food, potentially, right? And we start modeling
Right.
effects on the market. Right?
So I missed the very beginning of what you were saying.
Well, it's not just right that you can look at the Wikipedia and that's like not understanding the payoff. Here, I may actually be reaping the full benefit that I'm interested in.
There's no loss of the utility when somebody else uses it.
Yeah.
Yes, but when I meant the under provision part is that I'm not taking into account how much I'm benefiting you. That's the under provision part.
That means that the
I-
other person won't provide.
Right, so there's this is a case of externalities. And the fact that what we call is I'm not internalizing the externalities means I'm producing too little from the public point of view, not from my individual point of view. I'm doing fine. But from the public point of view, in terms of social welfare, I'm doing too little. But this is a bit of a digression into the general discussion of public goods. So let's get back to the network model. Okay, so I'm actually, maybe I will actually do just a brief rundown. So what are the contributions to the literature that I'm engaged in this particular research agenda? First of all, games played on networks, right? It's a new area. So this is, again, a general framework of games played on networks. I know there's some computer scientists out there or people who are trained in computer science. This is directly at the edge of computer science, so I'm going to have results, analytical results, which actually lead directly to computational problems. So how would we find, for example, the equilibrium that maximizes total public good provision, right? So we're going to see that. Again, this is a little bit more about games, and I think that I also, again, want to get back to the point is that another contribution is not just all of this wonderful theory that I'm producing, but that I am actually creating a new measure. I've discovered a new measure, which may be a key measure for understanding public good provision in network contexts. Or at least, if we don't want to use that precise measure itself as a number, we're getting some insights about what that means about network structure.
But the measure comes out of the theory and the assumptions of the theory, right? This is not an empirical measure.
It's, I'd say it's a, yes, it's a theoretical measure that one can then test.
Yeah.
So I'm generating predictions.
Okay.
Okay? Okay, so what I want to give you in the rest of the time that I have is a sense of the model, a sense of the equilibrium results and how it relates to this object called an eigenvalue. I want to show you some examples about adding the links, and then we'll wrap up. Okay, so in order to introduce the model, I'm going to introduce it in a formal way. So I've got n people, we call them agents, and they're choosing some action x. That's all you really need to know. There's n people, and they're choosing some level of action x. Okay, here's the network. So going back to this bit about adjacency metrics, I simply have a matrix. It's n by n, and the entries to each of these matrices, which we're called, is this little gij, right? So this is the ith row, the jth column is either a 0 or 1. If it's a 0, you're not connected. If it's a 1, you are connected. This is the base case that I'm describing. I could make it any number between 0. I can make it any real number, in fact, right? But I'm just presenting the base case. It's a symmetric matrix. There's some details. Okay, this is an important object. This is what we're calling this payoff interaction parameter delta. It's going to be a number between 0 and 1. And this is what I was saying can parameterize how much I'm actually getting from your actions. If it's 0, I'm not getting anything from you. What you do doesn't affect me whatsoever. If it's 1, what you do is just the same as what I do, and you'll see that. So this is some notation for payoffs. Okay, so it's a function of what I do, a function of what other people do, this payoff parameter delta, and the network G. Okay, so those are the ingredients I need. By the way, if this were just a plain old game, the G wouldn't be here. Okay? Okay, so adding the network is putting this G here.
Can delta be negative?
You sure can. So the base case, yes. So that these things can all be moved, so this can be any real number and delta can be any real number. I'm just presenting the basic case. And this basic case that I'm presenting is the one of strategic substitutes, the up and downs that I gave you. So I'm presenting the case of pure substitutes. Okay, but it's completely generalizable to any combination of substitutes and complements, so any delta and any g's. Okay, so here's a sort of an important thing to remember. This little x with an star on it, okay, this is what somebody would do if they were all by themselves. So if I had no neighbors, I couldn't learn from anybody, I couldn't enjoy anybody else's garden, this is the amount that I would do. Okay, so you just want to fix that as a number. We're actually going to make our lives easier and make that number just 1. Okay, so we're going to think about it as just 1. If I were all by myself, I do 1. You know, 1 amount of information or 1 amount of gardens. Okay, so what I'm going to do now is give you an example of a payoff function. This is the network version of the Bergstrom-Bloom invariant model. Okay? So to read through this, this is benefits. So this is individual I. This is individual I's benefits. His benefits are a function of what I himself does and what I's neighbors do. So this is all of the neighbors of I. So when this is a 1, I add in what J does. Right? And so I get this sum of what all my neighbors do, and I weight that by that number delta. So delta could be 0. My neighbors matter to me not at all. Or delta could be all the way up to 1, which means that whatever my neighbors do is just as good as what I do. And I am going to indeed play with that number. Okay?
How can that delta not parameterized by I also?
It could be. We could make that here. We could make, well, we can make delta I. There are some cases where we can make this a delta I. Some cases where we can't. We could just put delta inside here and just do everything with the GIJs, as long as we're still in the world of a symmetric matrix. And then we have some results for matrices that are not symmetric. Yes?
Do you know yet whether this generalizes for us that GIJ is continuous?
Yes.
And it does, right?
GIJ can be any real number. Okay. Okay. Oh, I'm not done. I forgot the cost. Thank you. Okay, so these are the benefits, right? These are the benefits that accrue to person I, and these are person I's costs. So person I, you know, the level of garden that I plant, the amount of garden they plant, or in the Foster and Rosenzweig example, this is how much land I put under HYV cultivation, right? That's this quantity here that I'm doing. There's a cost, C, for every additional unit I put under cultivation with HYV. Okay. All right, I was going to give a specific information example, but given the time, some math that could be behind this function, but I'm just going to skip that. There are other games out there that fit, so there's a Bergstrom-Bloom invariant game on a network. There's other games. Here is an example of another payoff function. I don't really need to go through it. This is just to sort of show to you that indeed we fit many contexts. So another one is a Cournot oligopoly. So if any of you took intermediate micro at some point, this is a Cournot game, fits this exactly. Now each of these games yields exactly this best reply. So what do we mean by best reply? So best reply is, think about what agent I wants to do. Agent I wants to get up to at least this target number, x star, right? And he can get to it by 2 ways. He can either do it all by himself, or he could rely on his neighbors. So he's going to, if his neighbors are doing this much here, remember this is what his neighbors are doing, then he's going to do the difference between those, because he wants to get up to x star. So what he does is the difference between what he wants and what his neighbors are already doing. Okay, that's all it is. Okay, so I'm going to plant a garden that's just the size that gets me up to this target level. And if my neighbors are doing it, and if in fact my neighbors are doing an enormous amount, then I can do nothing. I can just enjoy what my neighbors are doing. Okay? Now this structure is linear. So for the mathematics, the fact that this is a linear best reply is what gives us the class of models. Okay? But for the purposes of the discussion here, what you want to remember is that agent I is going to make up the difference between what his neighbors do and what he wants to get to. Okay? Because that's that number I showed you before. And that's some more notation. So we're going to set this number equal to 1, so I don't have to keep putting x star everywhere. Okay, so we're going to look for Nash equilibria. What are Nash equilibrium? Nash equilibrium is a levels of actions x. So this is like x, where's my little pointer? This is x1, x2, x3, x4, x5, x6, etc., such that each agent's best reply is satisfied.
On the prior slide, could we model hubris, basically, in an agent, that even when they see that their neighbors are doing more than their X star, they're like, you know, I think I can do better, right? If I did some experimenting, I might find a way to do even better than this information I'm getting from everybody else.
Yeah, but it's costly. Remember, that's cost to do information. So you have to remember, I could do better, but am I willing to pay the cost? And we're basically saying the benefits of more information are not worth the cost above that amount. That's exactly what X star is. It tells you the amount of information where to get a little bit more is not going to be worth the cost.
Okay, maybe I can ask, rephrase the question. Is there any condition for C such that your xi can be greater than x star?
No, X star is defined according to C. So what you want to do here is find the level of X such that the marginal benefits equal the marginal costs. And so that's what defines X star. So X star has incorporated in it C.
Is it possible for your marginal benefits to still be positive even though you reach and surpass that X star? So X star is what you...
Yes, but then the marginal cost...
In the absence of a network.
So marginal benefits are always going up here, but you know, they're eventually going to fall below marginal costs because this function is concave.
I understand.
Yeah.
But it's not obvious to me why that crossover occurs exactly at X star.
No, X star is defined to be the place where they cross over.
Okay, I have a different definition of X star.
So here it is. So here we go.
In the absence of a network.
Yes, it is. It's optimal in the absence of a network. But then, but so the way you want to think about it is it's based on this benefit function below it, where it is B, right? So take this out, right? And I look at marginal benefits equals marginal cost, and that gives me X star. But now I can so X star then is what I want to have on the inside of this. If I go up a little bit more than X star, right, the marginal benefits are going to be lower than marginal costs. Okay? Great. All right, so I was defining a Nash equilibrium for you. So a Nash equilibrium are the levels of action such that each agent's best reply is satisfied. So those equations I showed you, I want them to be satisfied. So given what all other agents do, agent I is playing his best reply, and this has to be true for all agents. So this is the definition of a Nash equilibrium. Okay, so now I want to get to some pictures, because how can you go through this long going to talk about networks and not show any pictures? Okay, so let's get some illustrations up here to really fix ideas. So I'm going to give you some illustrations with some basic graphs, and I'm setting this delta here equal to 1. So that key parameter, I'm going to set it equal to 1 for some of these pictures, just to get some intuition as to how these things work. So suppose we have a complete graph, and we might say that this is a complete graph represents an equal, densely connected society. Everybody is in the same position in the network. Everybody, there's nothing different about anybody here in the network. There's many, many, many Nash equilibria here. So you think about this guy here. Remember, his target is 1, because I've said now X star is 1. It's just a normalization, okay? So I've normalized X star to be 1. So here's Mr. Guy here in the corner. He does 1/4, and he's got 3 neighbors who do 1/4. So 1/4 plus 3/4 is 1, okay? So he's happy, and in fact, everyone's happy, right? Everyone's best reply is satisfied. This, of course, is also a Nash equilibrium. This guy here in the corner does 1, and his neighbors do 0, but they're all getting 1 from him, so they'll do nothing. So this is completely free riding, and this is complete distribution. So we have multiple equilibria in a complete graph. Okay? Now let's look at a star. A star is another canonical kind of matrix. It might represent some sort of hierarchy. We definitely have agents in different positions, different structural positions. We've got one guy in the middle. We've got people on the edge. Here, in contrast, there's only 2 equilibria. Okay? One equilibrium is where the center does all of the actions and the guys on the ends do nothing, right? Everyone's happy, right? Given what the other people are doing, everyone's playing their best reply. The other outcome, equilibrium outcome, is the guy in the middle does 0 and everybody around him does 1. That's also a Nash equilibrium. Okay? Now you look at that and you say, wow, but there's a, you know, up here, in some sense, what agents, this guy over here is not very happy, right? But what agents are getting is really the same amount of information, or public goods. But, you know, here, the amount of public good being provided is 1. Here, in the star, you can have an equilibrium with 1, or you can have equilibrium with 3. So these are very different in terms of the overall level of experimentation that's going on. Okay? Now, one thing that I may not have time to show you is that, is that when we're in this situation, I'm going to illustrate it for you now. I may not get to all of the math of it. If we were to look at a situation where we have multiple equilibria, something like this, either this one or this one, we might say, well, gee, what can I expect to actually happen? You're telling me there's 2 radically different things could happen. So we have a notion called stable equilibria. Stable equilibria are equilibria that, suppose I were to move what agents do just by a little bit, right? Where would we see the system, right? These best replies end up. And the answer is going to be this one right here. So think about, remember that up and down path I did? Right? There's ups and downs. Take this guy in the middle and say he just does a little bit less than 1. Right? Just a little bit less than 1. What are these guys going to do? Well, they're going to have to pick up the slack, right? These agents over here, they're going to do that a little bit more. Now this guy in the middle is going to say, well, gee, I've got 3 people around me doing something. Well, I'm going to go down. And then these guys go up, these guys go down, etc., until we reach this. So this is the outcome we should expect to emerge. Okay? And then what I'm later going to do is show you that this type of outcome is related to the lowest eigenvalue of the graph. It is not an accident, right, that we end up over here. It's related to the lowest eigenvalue of this graph. Yes?
So I'm following right to think that in any equilibrium state, like total utility for all the players would be 0, but in case it's more cost would be incurred. Right now, like I'm trying to figure out total social benefit.
Total. So what we want to do is here, no, in fact, these equilibria have very different total benefits. So this guy gets a benefit of 1, this guy gets a benefit of 1, this guy gets a benefit of 1, this guy gets a benefit of 3. Here, in this equilibrium, everyone's getting a benefit of 1. So this guy is really doing very well here. He gets a benefit of 3. So the benefits are much higher in this equilibrium. But then again, so are the costs, because we've got 3 people doing things. So then we're going to have to think about the cost versus the benefits, as you know we love to do. Sorry?
Cost is like linear in like amount of everyone has the same cost for providing linearly progressing amounts of the thing.
Yeah.
Right, so
Costs don't always equal. Why don't I talk to you a little bit later about that, okay? Yeah.
It's more a question to you whether I understand it right. Will it be true that in a standard variant case with complete substitutes, what we have is that complete free riding and corner case of equilibrium with one guy who wants it the most?
Yeah, so this is Varian.
And I think that
Sorry.
what you are doing, wait a second,
Yeah.
I understand. I think that what you are doing is my explanation sort of intuitive, that it's even more extreme in the network because the lowest eigenvalue is even worse than that. It's subsets. And
So-
they stop even faster. Will it be correct intuition or not?
So I'm not completely sure, but I can tell you this. Whoops. This case, this is Varian. This is the Bergstrom, Bloom, and Varian. This is it, because there's no, in some sense, there is no network here. Everybody's connected to everyone, right? So this is the base case.
But you could in reverse say that there is a complete network.
That's what this is.
So it is just a complete network.
That's what it is, yeah.
Yes, and when you have a disconnection, right, it should be that the effect is slightly less drastic
I don't
than the variance one. Because variance one is very
No, because here, see, here it is. right? This is the same thing in terms of total output and total welfare. Both of these are identical in terms of total public good provided, total welfare, meaning benefits and costs. So it's not true that just, having a network, having some disconnected agents, some agents who aren't connected, automatically puts you in another case in the complete graph. Some of them will give you it. So we can talk more, but I want to show you one more example. Actually, why don't I skip this example, because I want to get to this whole thing about this lowest eigenvalue. If I don't show you this lowest eigenvalue, I have not done my job this afternoon. Okay? So, sorry?
We're waiting.
Okay, so what I want to, the pictures are great, so I'm going to show you more pictures with this lowest eigenvalue. So again, what we do analytically is we solve for the equilibria for any g. So I can keep telling you, you give me a g, I can, any g and any delta. Okay? And this lowest eigenvalue is going to be key to the Nash and stable equilibria. So let me, so literally the results are the following. If the lowest eigenvalue of the graph, this is this number that you can produce from the network, is sufficiently big in magnitude, sufficiently small in magnitude, there's going to be only one equilibrium. Okay, we love this in economics, where you only get one equilibrium. You don't have to worry about there being multiple equilibria. So this eigenvalue condition is telling us when we have a unique outcome. And when we don't have a unique outcome, right, if we're not in this world, so now I flip the inequality sign, then the equilibria which are stable, remember I did this thing with this up-down path thing, the equilibria are stable are going to be the ones that are in these corners, these extreme versions. So whether or not we get this one person doing everything kind of equilibrium depends on the eigenvalue of the graph. Okay?
Can you give me an intuition that needs to have a higher?
Yeah, we're getting there. Yes, exactly. We're going to get there. Okay, so let me give you just some examples of the results, and then I'm going to show you the eigenvalue. Okay? So suppose we go back to a line. Now we have a line with 4 agents. What I'm going to do is illustrate the set of equilibria. Okay? So here, I know the eigenvalue for this graph. This line here is just an n by n matrix with 1s and 0s in it, and I can compute the eigenvalue and the lowest eigenvalue. And this is minus 1 over the lowest eigenvalue. By the way, for those of you wondering, the lowest eigenvalue is a negative number. Okay, so, all right. So this is this condition, and when this condition holds, there's one equilibrium, and here it is. That's it. There's only one equilibrium. Okay? And so that's it. There's just one equilibrium. Now I move to above my magic number, my magic eigenvalue number, and since delta is a little bit higher. And remember what delta is doing here is how much agents benefit from what somebody else is doing. So you're more in this world of substitutability, right? Some people do more, then other people will do less. And so you're going to get into this world where, now we can have a world where somebody's doing nothing and free riding on the other. Whereas when delta was smaller, right, and they weren't enjoying as much of what their neighbors are doing, you can't have that outcome. Okay? So it's a relationship between delta and the eigenvalue. So back to developing some intuition, this eigenvalue is giving another measure of substitutabilities. That's what it's doing here. Okay? And we're going to show you more of that later. Now, then delta equals 1, we get these extreme versions, right? 1 zeros everywhere, 0 1s everywhere. Okay? And there's one more thing we can learn from this eigenvalue, is that equilibrium up there, so I'm above my critical value, right? If I want to look for an equilibrium that's going to survive this stability notion, this way to select among multiple equilibria, this one where everybody's doing something does not survive. Okay? Because the substitutabilities embodied in the network are sufficiently big. Okay? So, and again, if we were to say, take this guy right here and make him go up, well, let's actually make him go down by a little bit so I can reach this one. He goes down by a little bit, these guys go up, these guys go up, these guys react, and we'd eventually end up here. Okay? All right. So that's just an illustration of, again, throw me any network, give me any delta, right? I can compute the eigenvalue. I can tell you what the equilibrium set is. Okay. Let me give you another example, and now I'm going to get a little bit more into the intuition. What is this eigenvalue? What is this thing? So now, all what I've done so far is I've shown you particular graphs. I've shown you the circle, I've shown you the star, I didn't show you the circle yet, but I will. I've shown you the complete graph, I've shown you the star, I've shown you the line. Now I want to get to graphs that actually are alike. There's many, many, many of these kinds of graphs, and they're called regular graphs. Regular graphs. A regular graph is a graph where each person has exactly the same number of friends or the same number of neighbors. Okay? That's a regular graph, and that's called the degree. All right? And so if you look at any regular graph, a Nash equilibrium is one Nash equilibrium involves everybody doing 1 over 1 plus d delta. And to make sure that that's correct, all you have to do is think of what agent I is doing. He's got d neighbors, right? So you multiply this number by d and delta, because delta tells you how much each neighbor affects you, and you get 1, right? So this is a 1 Nash equilibrium. So here is one regular graph. We've got 6 agents, right? We have 9 links, okay? So each agent has exactly 3 neighbors, okay? So that's one structure where we have, again, 6 agents, 9 links. And it's a regular graph. Each agent has exactly 3 neighbors. And this is one Nash equilibrium, because I've now substituted for this little d here, I've substituted 3. Okay, so here's another network which has exactly 6 agents, exactly 9 links. Each agent has exactly 3 neighbors, right? So it's the same in terms of number of people, number of links, a number of links per person, right? Those are all the same. This does not have more links going on. It's the same number, right? But you can see that it's very different. It's a very different structure, right? Yes? I'm going to tell you the lowest eigenvalue, which is what I've calculated.
Yeah, but what I'm wondering is,
so I don't know all of the eigenvectors for all of the eigenvalues, okay? So
I understand. What I'm trying to bring up is that for state distribution of of energy within an associative network or a neural network, or page rank in a graph, that's associated with the eigenvector of a graph, and it seems like you're capturing the dynamics of these.
right. So let me tell you that for each of these graphs, whatever eigenvector measure you want to put on each of these agents is going to be exactly the same, right? Because these are regular graphs.
Yeah. So I'm just wondering if predicted.
Okay, so I'll tell you what. I want to delay any discussion that's sort of well beyond what I'm solving. So the eigenvector for the lowest eigenvalue is relevant to these results. Okay, and I can talk about that in a little while. All right. So okay. So what was I saying? Again, what I want to impress upon you is that we have a society, say, or community, with exactly the same number of people, exactly the same number of links, exactly the same number of links per person. Yet the structure of the network is different, right? And you can see that by eyeballing it. And then I'm going to say, well, you know what? The eigenvalue, this really nice eigenvalue, is going to pick up on that difference and relate to the equilibria. So, okay? So one of our results is that an equilibrium is stable if and only if delta, that number delta, is less than or equal to -1 over the lowest eigenvalue. What I mean here by stable is, suppose I were to take this guy, make him do a little bit more, his neighbors do less, his other guys do more, they do less. Where do we end up? Do we go back to where we were before, or do we go off some other place? Okay, so it's a way to select among equilibria. Okay, so let's go through that exercise here. You write a matrix that represents this particular network, so it's a matrix of zeros and ones, and you calculate the lowest eigenvalue, and it's -3. Okay? So our result tells us that this particular equilibrium is stable for delta less than -3. Okay? So let's see what happens when I take this guy here and I make him do a little bit more. And when he does a little bit more, right, he's connected to these 3 people on the other side. They do a little bit less, right? When they do a little bit less, what's happening? They're connected to these people on the other side. They do more. They do less, they do more, they do less. And our eigenvalue tells us that if delta is bigger than 1/3, right, we will not go back to where we were before. We're going to diverge, and we're going to end up with either one side doing everything or the other side doing everything. So this condition tells us when we will see everybody participating in the provision of this public good versus some people, say one side here doing everything and the other side doing nothing. Okay? Now let's take this network. So this is the network up there, and when I again write this as a matrix and I calculate the lowest eigenvalue, I get a -2. Okay? And then our condition tells us, well, for delta less than 1/2, this is actually stable. If I make one guy do a little bit more and one guy, then I see what happens, I'm going to end up in the same place all the way up to delta equals 1/2. Now remember what delta is. Delta is how much what one player is doing is affecting the other people's play. So here, delta can't be too big, right? In order to sustain everybody doing something. Why? Because if delta goes over this level here, then people are enjoying what their neighbors are doing too much for this to be stable. This up and down pattern moves away. In this network, however, we can sustain everybody doing something all the way up to delta equal to 1/2. Okay? Now let's see why. What's the difference? Okay, so I show you, I tell you I've got this result, but let's actually take a look at it and get the intuition as to why that's true. Let's take this person here in the corner and have them increase by just a little bit. He's connected to 3 people, just like in the other graph. The other guy's connected to 3 people. So let's look. He's connected to this person, and this person, right? Now, these 3 people, having their neighbor doing a little bit more, are going to do a little bit less. True. But look at these 2 guys. They're connected to each other, right? So they can share this response. They're not going to go down as much, right? They can each go down by less than those guys did, right? So they're sharing the response to this guy going up. Are you with me here?
And in computer science, we just say it's a bipartite graph and everything's connected. Could you use that sort of theory for this alongside your eigenvalue?
I'm getting to that. Yeah, so this is exactly a complete bipartite graph, and I've got another 2 slides, and then I'm going to show you the relationship between the lowest eigenvalue and bipartiteness. So that's exactly where this is going. Hold on. Before I get there, though, does everyone understand the intuition of why, when I make this guy do a little bit more, these 2 guys are not going to respond as much because they're connected to each other? Whereas over here, none of the people who were connected to the guy who did more are connected to each other. So we have no triangles. Go back to triadic closure. We don't have triadic closure in this graph. Okay? So the lowest eigenvalue here is this -2, and so we can sustain an equilibrium where everybody is contributing for a higher range of this impact parameter delta. Okay? All right, so now let me get to this. Yeah. Okay. Were you asking a question? Oh, okay.
But how much of this up and down actually observed in the data? Because I think we're still talking about farmers. The ones who are experimenting are always the same. And they're the ones that have more assets or resources. They're the ones who are just fundamentally more curious. It has very little to do with utility, I think, to find it.
Okay, so I have a couple responses to that. First, this up and down notion that I'm describing is all happening in my analytical background. Okay? And what I'm ending up with is a prediction over what outcomes one should observe. Okay, and I'm saying you should observe, in fact, more often, right, in a graph that looks like this versus a graph that looks like this, some people doing everything and other people observing. So this up and down stuff is all a way of selecting among the possible equilibria that can emerge. And I'm saying in a graph like this, you're more often to see some people doing everything. Then let me just do a little bit on this individual heterogeneity. There are some people who are more curious. There's some people who like doing this stuff. I can do that too. I can make the cost function individual, right? I can make the delta individual. I can make the benefit function individual. I can play around with that, right? So I can incorporate individual heterogeneity also in the model. But given that I have 3 minutes left, I want to go ahead and give some intuition. You know, you mentioned the complete bipartite graph, and then I want to get to adding a link, because I've got wonderful pictures on that too. Okay, so I hope I've shown you this lowest eigenvalue does not depend on the number of links, right, but how they're exactly placed. So if we try and understand how does this low eigenvalue exactly relate to network structure, it is smaller when the links divide agents into fewer distinct sets, and there's more links between the sets than within the sets. So it's related to the bipartiteness of a network. So the one I showed you was what we call a complete bipartite graph. The agents are divided in two sets. There's links between, but no links within. Okay? There we go. So that's the result. Okay? So I want to get to this discussion, because I promised it, and I want to make sure I get there. So again, the lowest eigenvalue is related to the bipartiteness of a graph, and we have more results that I can discuss after the seminar. But now I want to talk about this bit about adding links. So if we have a new link between two people, what is going to happen? And let me give you just the example. So I'm going to show you two illustrations of this. So I told you already what the result is. When you add a new link, the total amount of public good provision is going to actually, it's weakly fall. It won't ever increase. Okay? And it's exactly this free riding problem. Right? But what are some of the things that we can see about that? So again, we can start playing around with, this is the type of thing we do, is we play around with what we might call representative network structures. So this is a representation. By the way, I'm back to the delta equals 1 case for illustration. So imagine I have two communities here. Imagine these are two villages. And these two villages are completely connected inside, but there's no links between the villages. Okay? And let me add a link. And now I'm going to add a link between two people, right? One in one village and one in the other. What happens? Well, in this particular case, total provision of public good does not change, actually. In this particular case, it doesn't increase. But so if it's just the same. But we have this interesting distributional effect. The people who have the link here, right, one of them is going to do really, really well, right? Because he has this source of new information, right? And so he, again, we're going back to this up and down pattern. He does less. Well, boy, you know, these guys over here, they've got to take up the slack, right? Because these guys here are not lucky enough to have that link to the guy in the other community. Okay? So these new links, while they might not be changing the overall pattern, are certainly changing the distribution. So that's one message. Another message is the overall link provision. Again, this is another thing we can do to play around with these graphs. So I'm now going to add links. And this is a model of, say, integrating a society. So imagine I start with a network which looks like the one over there. It's a circle. Okay? So I've got these guys organized in a circle. The way economists understand this thing is this agent over here, Mr. L. He is in a community with Mr. M and Mr. K, and we call these overlapping communities because M is in a community with N and L, so the communities sort of overlap. This is also called a local interaction graph. So I interact with people who are close by me in the neighborhood. So as we start off with this is the graph here, right? This is for delta equals 1. Again, I'm in the delta equals 1 case. So we're over the eigenvalue condition is holding, right? We can have 3 people providing the public good. You're going to have 3 people providing the public good, and they're going to be alternating within this circle. Let's add some links. So I'm going to connect these guys, and I'm connecting them in a particular way. So what I'm doing is I'm expanding each agent's neighborhood. So he's not connected to only these 2 guys. He's going to be connected across the circle in this particular way. And I'm going to do that for everybody. So this is the graph I get. Okay? So now everybody has 4 neighbors. And I've just expanded their communities to be bigger. But they're still overlapping. So it's still the same structure, but I've just expanded their communities. The equilibrium set here is I now have only 2 people providing the public good. Right? And then we can complete this even further. So now I'm going to complete the network. I now am in the world of a complete network. So this here is a complete graph. It's a complete network. And we only have 1 person providing the public good. And this is like the square, the complete graph I showed you in one of the earlier slides. So we see that as we increase the number of connections, this free riding increases and so on. In terms of welfare, we should be aware that costs are also going down, right? So then we're going to have to think about the costs and the benefits as we add links. Okay, but we should be expecting the more links there are to have lower provision of public goods, which may be good or bad given the costs. Okay, so I'm going to get to my conclusion slide. This is in case anybody wanted proofs. Okay, all right. There we go. They were all here just in case. Okay. So what we've done, and again, I should emphasize this is a long research program that I've been doing with Jan for many years now. And we're analyzing this large class of games, and that's what's very exciting about this. We have a unifying framework. And it's unifying because in some sense, all of these games have the same mathematical structure. They have these linear best replies. We solve for these Nash and stable equilibria for any graph and any payoff impact, and we relate the equilibria to the graph structure, which is this lowest eigenvalue. And we have some sense of what this lowest eigenvalue means when we sort of look at a graph. It's related to the bipartiteness of a graph. We're also able to do these comparative statics, which is like when we add links, what happens to the aggregate outcome. And then, as I said before, in terms of the analytics, we are contributing to simultaneous move and player continuous games, and we're at the edge of, now you get more of a sense of what I mean by being at the edge of analytics and computation. And we are generating predictions. So let me, a lot of you have been asking me other games, many, many more games. To do any combination that you want of G's and deltas. Here's the possibility that some guys have different costs. That's all possible. And you give me anything, and again, the lowest eigenvalue is still going to come out as important, and it's generating, I'm calling empirical predictions and possibly heuristics, right, for understanding public good provision, in particular network environments. Thank you.
Thank you very much. Before I open up to questions, because there's a lot of material we didn't see, is there a written paper that we can get access to?
Yeah, it's on the web.
It's on your website?
Absolutely.
Okay, great. For everybody to catch up. Okay, now I'll hand this off to the questioners.
You happen to address a domain I know a lot about, which is farming, and so I have lots of curiosity and kind of different kind of knowledge. So I'm not sure I buy your explanation of your answer to how to address individual heterogeneity, because that also is a network structure, and there's also games that one might play with different payoffs. So for example, with experimentation, right? There's a cachet to being the first person to try something in a village, and so that means if someone else tries, so could you address how you might address the interactions that might exist with the costs and the benefits?
Okay, so I guess this goes back to this question also of like, do I have the right model of individual incentives? And the answer is probably no. Okay? So this is going back to the question of, if we have utility over provision of a particular public good and everybody else benefits from it, we have that under provision. Remember that discussion we had? So this is, I think, in a similar vein of questions, have I correctly specified agent's utility? And I'm sure the answer to that is no. Okay? Then the question becomes, how should I amend that utility function? So some of the things might involve, for example, in a network context, is that I'm worried about doing at least as much as my neighbors because that gives me status. So now we're going back to sort of competitive gardening rather than this public good aspect of gardening. So I should be providing at least as much experimentation as my neighbors do because contributing to the community or looking like I'm doing a lot is actually a status objective. So one can incorporate that in a network model. So what I would want to do moving forward is think about utility functions that make sense in the network context. So there's lots of utility functions out there with status in it, which is their status. But now I want to make status related to the network, to my neighbors. Then I have to,
I think that this is a broader problem in economics. Everyone's got their own utility function, right? Because each individual has their own utility function. Yeah.
Right, so let me, I don't know if we want to get into this, but this is absolutely, and this is why economists fall back on having this very stark utility function, because then we can say, well, you choose your utility function and you'll get it whatever you want, and you over there, when you're doing your analysis, you choose your utility function, get whatever you want. And then, oh my goodness, chaos reigns, and what are we going to do? So one thing that we do is try and think about some some general way of extending the utility function. So that's actually what I've tried to do in the identity work. So in the identity work, I've said, okay, we think identity is important. And there's many, many, many different ways we could do this. In fact, status is identity. You know, we can do this. So we're going to actually say these are the 3 things that we think are important when one wants to capture identity or social groups within the context of utility. Okay? So a similar effort has not yet been done with networks. And in fact, that's one thing, you know, if I live long enough, that I'd like to do is marry the work on social identity with networks so that, you know, I now have a utility function. So who do I care about? It's people in my group, per se, right? So absolutely, this is a challenge, and this is both the strength and the weakness of economic methodology.
So let's suppose I have a new technology, pesticide-resistant crop or something, and I want everybody to start buying my seed, right, in the village, and I give you a geographic map and tell you to assume that everybody gets to see what their neighbors do, and I also tell you everybody in the village is an avid user of an online social network, and that I give you the graph of that so that you can see who's friends with who and who communicates with who. But of course it'll be an irregular graph, not like the ones we've looked at so far here. Would you be able to use these models to tell me who to target, right? Just give free samples to these 3 guys in the village, and sooner or later everybody will know about your new product.
The answer is yes. I haven't done it, but there are teams of researchers which are doing it. So I don't have that, I don't literally have diffusion here, as you've noticed, right? I have this creation of information that then flows, but I literally do not have, you know, one person adopts and the next person adopts and the next person. I don't have that game, which is more of a sequential move game. So there is a team of researchers which is studying, I think, more exactly your problem, and I could give you the references. And what they're doing here is they're exactly coming out with eigenvector centrality measures. So that was mentioned somewhere over here. So they're actually coming up with an eigenvector centrality measure. So the answer is that these tools, ultimately, these are the things we would want to do. So I might want to here say, if I'm trying to maximize economic welfare, again, economic welfare, I know all the problems with that, how would I design the network, right? Maybe I want not everybody linked to everybody, which was kind of a conclusion I got here. So the answer is yes.
John?
I'm curious about the algorithmic computational aspects of this model. So in fact, if you think about a social network graph, like a Facebook graph,
Sure,
right?
yeah.
Obviously, n is, you know, I don't know what number it is now,
Right.
700, 800, 1 billion,
Right.
much larger, but that's where the computational algorithmic aspect comes in. I'm wondering if this computation of this approach by using the eigenvalue metric, well, first of all, does that simply say that, yes, there's going to be lots and lots of equilibria,
Right.
as opposed to one? I mean, I think that probably
Right.
is going to be
Right.
the case here. But is it possible to use your approach to say that certain equilibria are more likely than others in a much larger graph?
Yes.
Beyond the small
Yes,
canonical
so
ones?
one of the
what
things-
can you say? What
Yes.
type of insights
Right.
do
So
you have?
First of all, is that this eigenvalue number, this eigenvalue condition, in the world of multiple equilibria. So suppose there's the world of unique equilibria, and then there's the world of multiple equilibria. And in the world of multiple equilibria, there's an eigenvalue condition which can throw away a lot of them as being not stable. So we can greatly reduce the dimensionality of the problem. Again,
Yes.
we're still in the world of a billion users, right? But we can greatly reduce that. So we can go, go from, I don't know, we've done some numbers on this.
Okay.
It would be kind of cool, actually. That would be an interesting computational issue to see if once we eliminate the unstable ones, how much have we reduced the set? Okay, we haven't done that, but we know it reduces it by a significant amount.
Yeah.
That's one thing. The other thing that we've done is we've gone around and said, and this is not presented here, I'm not even sure we'd find it in the paper, but I can give you references. I mean, it's in our working paper, right?
Okay.
It didn't end up in the final paper, but in our working paper, we looked at ways in which we could say, are there certain people in this network that we know are never going to do anything?
Mm-hmm.
Right? And we know what they kind of look like. In fact, they're very well-connected people.
That's right.
Right? because they have lots of sources of information. I know you might think, but wait, the well-connected people are doing the information, but not the really, really, really well-connected people, right? So there's sets of people that we can eliminate as being part of the stable equilibria. So we can again sort of restrict the set of agents that we need to search over. But we have not really, the absolute dimensionality of the problem is still huge, right? Yep. So yes and no.
Great, thanks.
One last question.
This seems like a really significant result, so congratulations. I'm wondering what the process was that you got to it by.
Oh, that's a really interesting question. Yeah, it's so we did not start this research saying, gee, I want to find the lowest eigenvalue as the answer to all our woes. No, that's not how we do this. So I was very honest in going through the discussion. The motivation was looking at this economic environment. We spent a lot of time looking at Foster and Rosenzweig's paper. We spent a lot of time reading outside of economics. We built our very first model of network public goods, right? Which is a special case now we know. It's a special case of the model I've presented here. Then we realize that there's actually a general model, and as we're doing this general model, we start actually combining different techniques to attack this problem of looking for the equilibrium set. And we're actually borrowing techniques from computer science. So it's actually the theory of potential games, for those of you who may know that theory. So we're combining the theory of potential games, and we realize, oh, gee, this is actually a potential game. Again, it was kind of all we need is one of our games in our class to be a potential game, and then we can use our theory. It's like, oh, wow, that's a whole breakthrough in and of itself. And then when we modeled, this is literally what we did, and you look at the mathematics of the potential games, and we relate the Nash equilibrium conditions to the conditions for potential games, and lo and behold, the lowest eigenvalue pops out. And there it is. And then we said, wow, that's really cool. But what does it mean? Right? So we didn't stop there and say, gee, this lowest eigenvalue pops out, this really cool number. Then we attacked the question, well, what does it mean? So if I look at a network, what is this lowest eigenvalue telling me about what the network looks like? And that was a whole another year of trying to figure that out, right? So the fact that it's related to the bipartite structure and exactly how things interact is a whole other process, right? And so then we're at that point, and then we're now thinking of application. So again, we want to bring this back to our original motivation, right? We started worrying about public goods. Let's actually now go back to specific environments and see if we can generate these predictions. So that's the sort of full cycle of the research.
Thanks.
That's a great place to end. Thank you very much.
Well, thank you all very much for your questions.